So today we'll be talking about differential privacy and how to build differentially private machine learning models. So before we start, can I get a show of hands to see who here has heard of differential privacy before? A few of you, have you built differentially private machine learning models previously? All right, this is good. So hopefully you'll get something out of this, and hopefully you'll learn a bit more about differential privacy. All right, so regardless if you know or not, I think we're all here today because we'll answer yes to this question. We all believe that privacy is really important. And as scientists who are building machine learning models, we're really here to protect the sensitive information that we use to train our machine learning models. And we all agree with that, right? All right, so for today's agenda, I'll quickly introduce Georgian Partners and what we do. And we'll dive right into provable privacy or differential privacy. And I'll show a package that's available right now, the TensorFlow privacy package that you can take and use to build differentially private machine learning models. And I'll close this talk with a real-world application of the differentially private machine learning models. All right, so Georgian Partners, we're actually based here in Toronto, and we're a growth stage venture capital firm, and we invest in software startups all across North America. So we have three thesis areas that we focus on: apply artificial intelligence, conversational AI, and trust. And so what we do with our portfolio companies is that we engage with them and we help them to adopt these technology trends. And we do that with what we call the impact team, which is what I'm part with. And so we're a team that's composed of scientists and engineers, and we engage with our portfolio companies on different research projects, what we call applied research at Georgian Partners. And what we're really trying to bring here is to bridge the gap between academia and the real world, because we believe there are a lot of really valuable researchers out there, but there's kind of this gap between academia and real world. So we really hope to bring these state-of-the-art algorithms to our portfolio companies. And as you might have guessed, differential privacy is one of the active research areas that we focus on. All right, so with that, we'll dive right into privacy. So privacy is kind of a buzzword these days. Everybody's talking about privacy. There's lots of definitions about privacy, but can we somehow measure it? Can we somehow put it so that we can measure the impact of the privacy? Can we prove that we have privacy in our algorithms? So with that, I like to start with a little exercise. So imagine if I'm a data collector and I like to learn how many people in this room have cheated on the exam before. Now, if I ask you this question, you might think this is sensitive, and you may not want to share that with me, right? Okay, so let's do this little exercise and see maybe you're more willing to do so. So in your head, pick a random number x, okay, so between 1 to 10, all right? And if this number is odd, then when I ask you this question, you have to answer truthfully, all right? But if that answer is even, all right, then think of a second random number in your head between 1 and 10, okay? And if that second number is odd, then regardless of what your true answer is, just answer yes, okay? And if that second number is even, then just answer no, okay? You all got that? All right, so let me ask this question. Who here has cheated on an exam before? Raise your hand if you answer yes. A few hands. Okay, looks like there's maybe 30 to 40% of the people here. So what's happening here? What happens is that, well, there is a lot of randomness. So half of the population here actually gave me a random answer. And if we imagine this like random number is completely random, then we would expect that 50% in this population would answer randomly. So that 25% of the answers that I got here would be a random answer. And so what we can do is we can sort of backtrack. So say there were 40 people, 40%, then 25% of those are random answers, then 15% actually really answered true. So that if we multiply by 2, then we get around 30%. So then it seems that 30% of the population here have cheated on the exam before. And just to let you know, the surveys out there actually says that 60% of the people would have cheated on the exam before. So it looks like we have a really wild crowd here. But what's really happening here is that what we're providing to users is something we call plausible deniability. So what's really happening is that I've asked you this question, but you can tell me that, well, it was a random answer. So what I've done is I've learned information about the population without learning individual information. So I actually don't know if you raised your hand because it was a true answer or it was just a random answer. All I've learned is information about this population. And this is what I really want to achieve. I don't want to learn any sensitive information about any individuals. And so this exercise is actually called randomized response, and it's actually existed for half a century in the marketing literature. And from this, Cynthia Dwork and other researchers have coined this term of differential privacy. So with this inspiration of the randomized response, and what differential privacy really is that given two neighboring data sets, D and D prime, with only one record or one user that differs between D and D prime. With any randomized algorithm, and what differential privacy really provides is that the outcome or any event happening of applying this algorithm to D should not change that much when we apply it to D prime, which is saying that whether you participated or not in this training data set or in this data set, the outcome should not change that much so that you as an individual, you can tell me, you can say that, well, like with my participation or not, it shouldn't change that much, so you don't know whether I participated or not. So this is the whole philosophy of differential privacy. But just note that, so we have this e to the epsilon multiplicative factor here. And so this epsilon is what we call the privacy budget. So it's not a binary term. So it's not like we turn it on or turn it off. It's really a scale. So the smaller your epsilon is, the more privacy you would achieve in your algorithm. All right? OK, so then how is differential privacy achieved? I guess if you think back of the exercise that we did earlier, and I guess this slide kind of gives it away too, well, we add random noise, right? And this can be done through different mechanisms, such as Laplacian mechanism, Gaussian mechanism. And we have to do it based on the sensitivity of the algorithm that we're applying. All right, so a quick definition of sensitivity. So the sensitivity of any algorithm on a data set is that how much would your output change if you had the addition of or the removal of one single user or one single record from this data set. So let's think about the exercise that we did. We tried to count how many people. So then counting has sensitivity of 1, right? So for example, we had 100 people here, and with the addition of one extra person, then the counting, the final output would change by at most 1. But if we do counting rounded up to 5, then it has sensitivity 5. Okay? All right, so then with this in mind, with the definition of differential privacy, then how do we apply this in machine learning? So let's think about one particular model, logistic regression. So let's think about what we're doing really here. We're trying to minimize this logistic loss over our data set. So really, this is just a randomized algorithm. It's a lot more complicated than counting, but it's still just a randomized algorithm. Then what is the sensitivity for this? Well, it's really hard to calculate. It depends on the data set, and there isn't really a one number that we can really define. So then what we can do here is to use worst case analysis and bounds to bound our sensitivity and add noise according to that sensitivity. Then during a machine learning pipeline or process, how do we add the noise? How do we really achieve differential privacy? Well, because machine learning has multiple steps, differential privacy can actually be achieved in multiple steps. The noise can be added to multiple steps. You can inject noise directly into your data set, like what we were doing in the exercise. We just flipped half of our answers into random answers. You can inject it to the training process, to the optimization process. You can inject it to your gradients. You can add it to your computed weights. You can also inject it to the aggregation process. So there are multiple ways of doing so. There exist multiple algorithms and multiple ways of doing that. All All right, so with that, as a high-level overview, I'd like to quickly introduce different TensorFlow privacy. So because when you're thinking about doing private machine learning, you don't want to think too much about the sensitivity of the different algorithm. So this is why we've built this package out there that you can just take and apply it to your machine learning models. So the TensorFlow privacy library is available as a sub-package under the TensorFlow that you can take a look and check out. There are multiple algorithms within this privacy package that will apply differential privacy at different stages of your machine learning models. And for today, I'm quickly going to focus on this bolt-on differential privacy package. So the bolt-on differential privacy sub-package is, well, if you remember this graph before, so it adds noise to the weights. So compared to the other algorithm, it adds noise to the weights. And so what we found is that by doing that, you can just train your models, and then at the final step, you can add your noise, and so your differential privacy becomes like a bolt-on to your machine learning models. And by doing this, you still keep your runtime, the optimization process, approximately the same. And with experiments, we've seen that this also performs very well. And so currently in the bolt-on sub-package, what we offer is both binary and multi-class classifications for logistic regression and support vector machines. All right, so how do we use it? So what bolt-on sub-package is really just a wrapper around Keras. And it's really like, so when you're building a Keras model, for example, so you can import the bolt-on models. You can declare a classifier just as a bolt-on model. And you just specify a few privacy parameters. And when you're compiling your model, you can specify actually any optimizers that Keras supports. And when choosing the loss, you just have to choose the differentially private loss. And then you have to pass some of the differential privacy parameters. And you just train the model as what you would typically do with a Keras process, except that you just have to pass in this extra epsilon privacy budget. And so in the package, there's lots of other tutorials. I really encourage you guys to download it and try it out. And you can just build a differentially private model very simply. All right, then I'd like to just quickly go over a real-world use case of differential privacy and how at Georgian we've employed it. All right, so the cold start. So Bluecore is one of our portfolio companies. They're a marketing automation firm. And what they do is they build predictive models for each of their customers who are retailers. So think of your Nikes, Under Armours. And the problem that they're facing is this cold start problem, which is when they onboard a new customer, sometimes they need 3 months to collect enough data before they can build a predictive model that's good enough for this particular customer. And during this cold start period, then they're really not making any money, and they're just losing this precious amount of time. So, well, then we started thinking, can we leverage the models from the previous customers? Well, because a lot of these customers are similar, perhaps some of their users are even the same, can we leverage the knowledge that we've learned previously? Well, then that sort of we get into, well, perhaps Nike needs to share data with Under Armour, and of course they don't want to do that because they're competing partners. So then we started thinking, how about we employ differentially private models? If we promise that the model that we are training for Nike is differentially private, and we share this differentially private model to Under Armour, are they willing to share that information? And so this is the sort of work that we try to, we apply with differential privacy. So then what we've built this framework is that for each of the different partners or each of the different retailers, we train a differentially private predictive model. And because each of these models are differentially private, then we can aggregate these models together to provide lift for the predictive power for each of the different partners. And as a result, so what you can see here are the orange bars is the model performance of non-aggregated and non-differentially private models before. And the blue bars are the aggregated and differentially private models afterwards. And you can see that there is a big lift for the majority of the customers. All right. And so while doing this project, we've encountered quite a few challenges. Well, the first big challenge is legal marketing. Because differential privacy is not that easy to explain to people, and it's not a common known approach to privacy, it's really hard to convince the customers that this machine learning model is going to be private, it will protect your data, and then so can we share this model with others? So this entire process of explanation is quite hard. And also, how do you translate the privacy budget? So how do you translate that epsilon number into some kind of business case? Like does 0.1 equals to, like how do you translate that to dollar amount? This is also something that's been very challenging for us. And if you're applying differential privacy, this might be a challenges that you run in as well. And in terms of the technical challenges, well, I guess like one thing that you think, so I didn't really mention is that when we inject noise into machine learning models, well, inherently, because we're adding a lot of randomness, the performance of your models will decrease. And so then we really need to think about the balance between performance of the models and privacy, and the privacy that you want to achieve in these models. So in this particular use case, what we've been able to do is to aggregate differentially private models to really boost the performance. But if you're just applying differentially privacy to one specific machine learning model, you can expect the performance to go down. So then that also becomes a business decision. Do you want to trade off performance for privacy? And so in this data set that we tried, so we just run a quick experiments to see by varying the privacy level, so by varying epsilon, what is the performance that we get? So you can see that, well, of course, with a much smaller epsilon, then we get a almost useless classifier. But with an epsilon to roughly around 0.1, we can get a pretty good enough performance. So then, again, this will come down to a decision between performance versus privacy. If you didn't get much out of this presentation, hopefully you take these few points away. So differential privacy provides privacy guarantees for individuals while allowing data scientists, allowing people to learn information of the population as a whole. Okay? But differential privacy does not protect against all attacks. It's really just about protecting individual information, sensitive information. But it could actually lead individuals to share more data. So when I asked you this question, have you cheated on the exam before? Maybe you were reluctant to answer me initially, but if I added this randomness factor, maybe you were more willing to share that information with me. It could decrease performance, as we've seen in the last graph. But in SaaS companies where there's this cold start problem, even though that the single model's performance may decrease, but this actually opens up a lot of opportunities such as transfer learning, aggregation of data, and this will allow you to perhaps increase and boost model performance. And the one important thing to really understand for differential privacy is that you need to really balance between performance and the privacy. And finally, just check out this TensorFlow privacy library. It's available out there. Just clone it to your repository, play around with it, and start building differential privacy models. So thank you. Some references.
If you want to do a recommendation for the first 3 months, how would you know this user in this company is that user in that company when you share both companies' data?
Well, so the models are shared, right? So for example, I can train a model for Nike, and then as users come in through Under Armour, I can use Nike's model to make predictions for Under Armour's users.
anonymously, so you don't know that this user here is that user there?
No.
Oh,
no.
okay.
Yeah.
Okay, thank you.
Thanks. Yeah.
Thanks for the presentation. So how does this deal with outliers and hierarchical data? So if you have, let's say, product and then sub-product category codes, for example.
I'm sorry, it's really hard to hear.
Can you just repeat
Sure.
the question?
So I guess the first question is how do you deal with outliers? Because even if you add noise, depends on how much noise you add, they could still be outliers. And the second question is if you have hierarchical data. So if you have, let's say, product categories and then subcategories in the data, how are you going to add noise to those while preserving that hierarchy?
So for the first question was around
Outliers.
outputs, right? Outliers. Well, so this is what I was trying to get the point across is that you're definitely going to lose in model performance. And so the randomness, as you said, will create some outliers. And so I guess the point is that there's really no counteract against your loss of model performance. And you really just have to sort of balance between how much noise you want to add. And this also depends on the sensitivity of your data set and also on the sensitivity of your machine learning models. And actually, in some cases, I've seen some research on saying that differential privacy could actually help with your machine learning models because some of the models will overfit to your training data. And so what differential privacy by introduction of like random noise is sort of generalize a little bit your models as well, and it could generalize better. So these are also experiments that you have to run with your data set and your models to try them out. And the second question was around categories or?
Yeah, so hierarchical data. So let's say you have product categories and then you have subcategories and so on and so forth. So how do you make sure that you preserve that relationship in the data?
So then so for example, with the bolt-on package, it actually just introduces a noise only at the end of your training weights. So while training, you still conserve all of that relationship. You just keep that away from the people that you don't want to share the data with. And after you've trained the model, the noise is only injected to the weights of the models. So then, you'd still sort of keep that relationship, but you might still have some randomness after you've trained the model. Yeah, thank you.
All right, and one
sure.
more question here.
What's the advantage of sharing a model for a company?
Can you just repeat the question? Probably speak closer to the microphone.
I mean, what benefit the companies get if he shares his model?
So for the specific company, I guess like if we go back to this slide, so by sharing your data with other people, well, like you're also getting the advantage of the other people's data. So for you, your particular model the performance for your model is also improved because now we have more data and we can leverage the information for multiple customers, multiple companies. Yeah, thanks.
Yep, sure, go ahead.
Hey, so this is like a follow-up question to that question.
Sure, yeah.
But I was going to ask this, so I get to ask the second half of it. So let's just take two companies that do something very similar, Nike and Adidas, right? So I can be Nike, you can be Adidas, and then a third person says, why don't you share the data in this sort of method? How would you have that conversation? Because I might say, no, like I don't need them. I'm going to dominate the market entirely.
Yeah, so this is definitely one of the challenges that we faced. And unfortunately, I wasn't the person to talk with the customer, so I wouldn't be able to fully answer your question. But I think it's just to show them data that, by sharing data amongst us with this third party, as this third company starts collecting data, they can also share data with us. So then we can also benefit from the users from that third company as well. So I think it's just that conversation that with sharing data, but in a private manner, we can boost the performance of all of our predictive powers. Yeah.
So you would speak in affirmative, positive language that everyone's going to benefit. There's no because I can't help but to think that once you're as big as a company like Nike, anyone existing is taking away from your market share. Whereas in other industries like I don't know, hotel industry, like it's not that. I would appear not so.
Well, I guess like it also depends on the use case. For here, for example, we're just trying to predict whether a person is going to purchase something or not. It's just the propensity to purchase or not. And so then in this case, they're not really competing. It's not like we would recommend a customer to buy Nike versus Under Armour. So it's really just the predictive power of each of the different individuals. So then so I guess it really depends on the use case as well. So there's definitely use cases like you said that they may not be willing to share that data because you might, compete with me and you might steal my customers. In this particular case, where we're just trying to build a predictive model, it's not a huge threat, I would say, for the companies. Okay, perfect.
All right, thank you, Chang,
thanks so
and
much.
thank you, everyone.